So let me just briefly introduce Stefano. So he's an assistant professor in computer science at Stanford and also affiliated with the Artificial Intelligence Lab. So he's developed, so he has had many awards, NSF Career, ONR Young Investigator, best papers in different conferences, AAAI, UAI, CP, and so on. So he works in a number of areas, so graphical models, statistical modeling of data, combinatorial optimization, robust decision-making. And so perhaps recently he's started working, interacting with Slack and people in more of the physical sciences. And so today he's going to talk about some of the application of his work in the physical sciences. So thank you very much, Stefano, for giving this virtual presentation. Thanks.
All right, thanks. So can you see the screen?
Yeah, perfect. Yeah, it's
okay.
working. Yeah.
And you can hear me well?
Yeah, no problem. It sounds good.
Perfect. All right. So yeah, thanks a lot for the introduction. It's great to be here and at least virtually, and tell you a little bit about the work that we've been doing, both on the machine learning side of things in terms of developing new algorithms and methodologies, but really inspired by applications in the physical sciences. And so I'm going to be talking a bit about how we've been using vision optimization and machine learning to accelerate the scientific discovery process in the context of optimization of batteries, up at Slack, at LCLS, an X-ray electron laser, and more. Right. So the setting is that, as you probably know, in the last few years, there's been a lot of progress in AI and machine learning. In computer vision, there's been a lot of improvements. We've been able to build systems based on deep learning that are pretty good at recognizing objects, activities in images, videos, and they perform comparably to humans on pretty challenging benchmarks like ImageNet. Similarly, speech recognition, we have systems that work pretty well, and now we're on hundreds of millions of devices all over the world. In reinforcement learning, we've been able to build computer systems that can beat the very best human player in complicated games like Go, chess, and so forth. And it's really the entire field of AI that is booming. We've seen a lot of progress in machine translation, theorem proving, question answering, robotics, and so forth. Right. So what's next? One challenge that I think it's very exciting to think about is the one that was posed by Hiroaki Kitano a few years ago, this challenge of trying to build an AI techniques that are going to be able to make some kind of scientific discovery that is worthy of some recognition, like a Nobel Prize. Right? I think that's of course like super hard, and it's very far out at the moment, but I think it's an exciting problem to think about, both because as we make progress and as we're able to accelerate the scientific discovery process, then I think that there's going to be a lot of positive impact on the progress, the pace at which we develop new technologies, and lots of impact on various kinds of economic aspects. But not only that, but also because I think it's so hard. Science is perhaps one of the last jobs that will be automated by artificial intelligence, because it's such a difficult, such a complicated process that it poses some really interesting challenges from a methodological, from an AI perspective. If we are ever able to do it, then I think it would probably mean that we've managed to really build a system that has some aspects of what we think is human intelligence, human cognition. If you think about scientific discovery, as I mentioned before, it's a really complicated process. It involves, of course, human intuition, human ingenuity, creativity. We need to come up with the right ideas, the right problems to think about. It involves models, it involves coming up with the right abstractions, thinking about the right variables, the right mathematical formulations, the right statistical tools to capture relationships between variables. Of course, it's a highly inductive process, so we need to figure out how to deal with data. We need to figure out how to, at the end of the day, we care about the physical world we live in, and so we need to figure out how to go from observations to knowledge. And so we need to figure out how to think about the inductive process of going from data, from observations to new hypotheses. But also there's often a rich amount of domain knowledge. I don't think we would ever want to start from scratch as we develop AI tools that can accelerate the scientific discovery process. We really need to figure out ways to incorporate all the things that we already know about the physical world, about math, about physics, about chemistry, and so forth. And so there's also like a deductive aspect to it. It's not just induction, there's also deduction. We need to figure out how to reason about theorems. We need to figure out how to reach conclusions from some hypotheses. And we kind of like need to combine all these aspects in a really potentially very, very complicated way. And so kind of like, I think if we are ever able to achieve this, then it would mean that we've made some significant progress in terms of this fundamental question that we have in AI, which is how do we represent knowledge, rich, complicated knowledge about real world physical processes? How do we reason about it? How do we draw inferences? How do we make predictions? How do we acquire this kind of, how do we represent the knowledge in a compact form that is potentially something that we can convey to a human? How do we do this by combining data, combining observations, combining experiments with domain knowledge, with all the information that we already have encoded in text, in equations, in formulas, in variants, and all the rich scientific literature that is available today. And so this is a really like a really grand challenge, a really difficult problem to think about, not something that we're anywhere close to achieve, but it's an interesting problem to kind of think about and try to make progress on. And so what I will do today is I will talk about some of the work that is kind of like loosely inspired by this idea of trying to make machine learning systems more useful in the context of scientific applications. So we'll focus on three parts. I will talk about some work that we've done on modeling uncertainty, this key problem of kind of making sure that the systems that we build, they are aware of what they don't know, which is a critical thing that we really need to be able to deal with if we want to think about making predictions, using these systems to make decisions, figure out what kind of experiments to do next to reduce this uncertainty, and so forth. And then I will talk about how to use these kind of ideas in the context of optimal experimental design. I will show you how we've been able to drastically accelerate the process of optimizing battery technologies using machine learning systems. So a closed loop kind of experimental pipeline where experiments are designed by AI systems, data is collected, it goes into the cloud, it's analyzed, the hypotheses are being refined by the system that then designs new experiments, and all in all, we were able to get some significant improvements in terms of the time required to find good charging protocols for batteries. This is a paper we recently published in Nature a few weeks ago. And then I will talk briefly, there's probably not going to be enough time to talk much about that, but I will touch on how we've been thinking about incorporating domain knowledge and how to not just use purely data-driven approaches, but how to incorporate simulators, how to incorporate invariants and constraints that might come from physics or common sense knowledge that we can use to kind of bootstrap the learning and make it more efficient. right? And again, kind of like these are problems that are inspired by real world scientific applications. And so there's going to be kind of two components. There's going to be some work on the technical side of things and developing new algorithms and new methods in ML, but then also some discussion about the applications in battery technologies, free electron lasers, and so forth. All right, so let's get started with uncertainty. Why is uncertainty useful? Well, uncertainty, being able to capture what we know and what we don't know, is really useful in imperfect information scenarios, which is basically always the case in any real world application. Whenever we're trying to model a physical system or any kind of real world system, we never know exactly how it works. There is always some uncertainty. Maybe we don't know the physics of it. Maybe we know the physics, but we don't know the parameters exactly. Or maybe there are some quantities that we don't get to observe. And so we have to deal with that uncertainty. And really knowing, being able to capture that, being able to deal with this uncertainty is critical if we want to use these models to make decisions. If we need to figure out what sort of experiment do I do next, we need to have a good sense of what kind of predictions we're confident in making, which ones we're not. If we're evaluating an engineering application, we're evaluating different ways, let's say, of charging a battery as fast as possible. We need to be able to make confident assessments about which protocol is better. So we need to be able to get not just make point estimates and come up with a single number, but we really need to be able to capture some notion of how confident we are in the predictions that we make. Now, how do machine learning systems deal with uncertainty? Well, typically, machine learning systems are based on data. Of course, there's also some prior knowledge that is incorporated, especially if you're thinking about Bayesian approaches. But fundamentally, the idea is that we have some kind of training set. Here, for simplicity, I'm thinking about a classification, a binary classification setting, and we have a bunch of data points. Each data point is represented by a set of features that we're going to denote xt, and then there is a label. As I said in this simple example, the label is binary. So in this case here, you can see a simple training set with 4 data points represented by these people. And we have 3 positive examples and 1 negative example. The third one, the third man in this line of 4 patients. And what do we do? Well, machine learning systems are typically they are probabilistic in the sense that they will make a prediction for how likely the system thinks each of these data points is to belong to the positive class. And these probabilities, they are typically a function of the features of the data point and some set of weights or parameters that basically represent the statistical model. And so maybe we start with a set of weights, W1, and with that set of weights, with that kind of statistical model, the model will make some kind of predictions. We'll come up with some probabilities that each data point belongs to the positive class. Maybe the initial probabilities are like 20%, 30%, 80%, and 10%. And now clearly these are not good predictions. We would like the system to assign high probability to the positive examples and low probability to the negative examples, which is kind of like the opposite of what the system is doing right now, because it's assigning 80% probability to the only negative class and let's say 20% and small probabilities to all the positive examples. And so there is some kind of loss function that captures how well these probabilities is matched with the labels. And typically what you do is you train the system by optimizing this loss function. And so you change the weights to change the probabilities and try to make them more consistent with the training set. So maybe we go from W1 to W2 by taking gradient descent or whatever algorithm you want. And these probabilities are a little bit better because now it's assigning high probability to the positive classes, but it's still kind of like making a mistake. It's assigning a 60% probability to the third example. And so maybe we do some more updates and we end up with our final model that will assign these probabilities of 80%, 90%, 20%, and 70%. Right, so now it would be nice if we could think of these probabilities as a notion of how confident we are in the prediction that we're making. And one way to think about this is that we would like it to be the case that these probabilities are calibrated. And what this means is that if these probabilities kind of like mean what we think they should mean, then it should be the case, for example, that if we look at all the examples where the system predicted 60% probability, then it should be the case that among all these examples where the system is predicted 60% probability, then it should be the case that roughly 3 out of 5 or 60% of them are actually positive. Right? So if you're thinking about predicting the weather, one way to see whether probabilistic forecasts are good is to say, well, let's look at all the days where the weatherman predicts 60% probability of rain, and then you check how often among those days it actually rains. And if the predictions mean anything, then it should be the case that the empirical rate of the outcome actually matches the prediction.
Stefano, can I ask a question here?
Sure.
Yeah, so the 60%, can you clarify a little bit what this is? This is, in the previous example, you were showing, I don't know, maybe those were patients. Yeah. So it sounded like, okay, I mean, maybe somebody is sick or somebody is healthy, and then, you know, you assign a certain confidence, you know, the neural network that makes a prediction as to whether, you know, the patient is sick or healthy, and maybe you get 60%. But this is different from saying that you have a stochastic system where you have some given certain features, then there is a 60% chance that the person is healthy or sick. So could you clarify a little bit the meaning of this, like which scenario you're in?
So the scenario is that there is some underlying process that relates the label to the features, and you are coming up with a model of that process, let's say through a neural network, that will take different inputs and will produce probabilities.
But this map is deterministic.
Yeah, it's deterministic, but it's coming up with a probability, right? Let's say if there is a Bernoulli random variable, if you're doing binary classification, then the neural network will output the parameter of that Bernoulli random variable. And so it will say, oh, I think that for this X, there is a 60% probability.
Okay, all right. So it's a deterministic map, but the process is stochastic that you're trying to model.
Yes, the process is stochastic. Right. So let's say Y given X is a Bernoulli random variable with parameter P. Right. And the neural network outputs the parameter of the Bernoulli random variable.
Okay. Yeah, thanks. Yeah.
And you like it to be the case. Yeah, please do ask questions at any point. Yeah, otherwise it feels weird to not see anybody, and I don't get a sense of whether people are confused or not. And yeah, so we'd like it to be the case that these predicted probabilities actually match the observed rate, right? The observed fraction of people, let's say, that belong to the positive class. But it turns out that it's often the case that if you train, let's say, deep neural networks, the kind of probabilities that you get from these systems are not calibrated. They do not satisfy this property. Neural networks tend to be highly, typically they tend to be overconfident in the predictions that they make. They will say, oh, this image belongs to a certain class with 99% probability. So you cannot really think of these probabilities as a notion of how uncertain we are in the prediction. Just to give you an example, what you can do is you can really, and now just pay attention to the blue curve here. You can try to do exactly the procedure that I described, and you can look for every predicted probability, which is on the x-axis. You can try to check what is the actual empirical probability that you observe. And for a typical system, you might see something that looks like the blue curve. Ideally, you would like to see a diagonal line where the predicted probability matches exactly the empirical probability, but that never happens in practice. In practice, you see something like the blue curve, where there is a mismatch between these two things. And one way to think about what's going on is you can imagine a simple situation where you're just doing binary classification. You have blue points and brown points, and maybe you have a simple linear classifier that tries to distinguish these two types of points. And typically, in this case, the probabilities that the system will output will have something to do with how far away you are from this decision boundary. If you are on the decision boundary, maybe the probability is 50%, 50-50, high uncertainty, and the farther away you are from the decision boundary, the more confident you are that the point belongs to one class or the other. But if you think about what happens, it's entirely possible that if you think about a slice in this plane of points that are at a given distance from this separating hyperplane, it's entirely possible that the actual empirical fraction of red versus blue points that you see in that slice doesn't match the actual predicted probability. And that is what is leading to this miscalibration, that there is no way of actually getting these empirical frequencies that you see in the data distribution with the kind of probabilistic model that you're using to model this relationship. And so you might see something that looks like the plot that I have on the right, where there is a mismatch between the predicted probability and the predicted probability that you would like to see. And so the solution is that you can recalibrate this in a fairly straightforward way. What you can do is you can keep a held out data set, and you can learn a separate model that will try to map predicted probabilities to true empirical frequencies, right? So you can fit something like an isotonic regression shown on the rightmost plot, or any kind of even just a histogram kind of thing that will figure out that if when the model predicts 0.2, the actual probability is more like 0.1, then you can learn this mapping and you can apply it to the predicted probabilities so that they match the actual properties of the data distribution. Like on the leftmost plot, I don't know if you can see my cursor, but you see here that at 0.2,
we can see your cursor, yeah, no problem.
Yeah, the predicted probability is more like 0.1. So again, it's overconfident. It predicts 0.2, but the actual empirical probability is more like 0.1. So you would like to figure out how to stretch it and push it up and look it more like the green curve by using a separate kind of regression model. So this is a standard technique that has been used for a long time in classification. And the question that we were looking at is how do we do this for regression models? Typically, we often care about predicting not binary variables, but predicting real valued quantities. And again, we would like our predictions to be calibrated, right? So if we're using some kind of Bayesian system, like a Bayesian neural network, to make our prediction, maybe you have different design choices and you're trying to predict how well they will perform. We would like to give a sense of how confident we are in the predictions, maybe using confidence intervals or credible intervals. And again, we would like it to be the case that these predicted probabilities match the true empirical frequencies. So if your model predicts a 90% interval, confidence interval, then it should be the case that the true value is in that interval roughly 90% of the time. But as you see here in this real world example on the left, where I'm plotting a 90% confidence interval, it's often the case that the true values are outside this confidence interval. And so again, what we would like to do is we would like to recalibrate this system and look more like this, where it is true that roughly 9 points out of 10 belong to a 90% confidence interval. And so how do we do it? Well, in the case of a regression problem, we can think of it as a model that takes a feature vector xt as input. And now the prediction model will output a CDF, a cumulative density function ft, for the label given that particular input. So it's no longer like before a Bernoulli random variable, but we have some kind of continuous random variable that we're going to model using a CDF. Now, what does it mean in this case for the CDF to be good, to be correct? Well, if the model is correct, then it should be the case that if we apply the CDF to the random variable, to the true label, we get a uniform random variable between 0 and 1. Or perhaps the easier way to think of it is that one way to sample from this random variable y, which corresponds to the label for data point xt, is to invert the CDF, right? You probably seen this trick, this way of sampling from a random variable. If you want to sample from a random variable, you can randomly pick a number between 0 and 1, you can invert the CDF, and that will give you a sample from the random variable. Now, if you apply f to this expression on both sides, you're going to get this fact that basically f of y should be distributed like a uniform random variable, right? And so if our prediction model is correct, then it should satisfy this property. However, the challenge is that this is a very hard property to check because typically we only get to see one label for each input. And so it's very hard to actually come up with this empirical CDF. If we were able to get multiple measurements for the same input, then we could maybe do something like this. But if you get to see if in your data set each X is different, then you cannot really come up with this CDF. So our solution here is to look at a weaker property, which is average calibration. Right? If the model is calibrated for every input at the individual level, then it should also be calibrated on average. And what this means is that it should be the case that for every choice of your quantile P, if you look at the fraction of points, so if you have a data set of size T, you have T data points, for every quantile, for every P quantile that you choose, it should be the case that roughly a P fraction of your data points belong to that quantile. So for example, if P is 0.5 here, and this is basically the median, and it should be the case that roughly half of your points are below the medians that you predict at each individual data point. Right? If the model is calibrated at the individual level, then it should also be calibrated on average across data points, and so it should satisfy this property. And this is a property that we can check. This is a quantity that we can measure, just like before when we were actually computing empirical frequencies at different predicted probabilities. This is kind of like the same thing for a regression model. And so just like before in the classification example, you can take a model that will produce confidence intervals that are not necessarily calibrated. And you can look at basically how do the predicted probabilities basically match with the empirical frequencies that you see in the data. And so you can do this kind of plot where you look at different quantiles of these distributions. So each P here, each point on the x-axis basically correspond to a quantile, to a value of P in the previous formula. And you can check on the y-axis what is the empirical, basically cumulative distribution that you see for that quantile across the whole data set. So for example, you try P 0.5, like the example we had before. This is basically the median, and it should be the case that across all your data points, roughly half of them are below the predicted median. And in this case, it is roughly correct. However, if you look, let's say, at an 80% quantile, in this case, you see, again, that there is sort of like a mismatch, and only maybe 0.7, maybe 0.65, whatever is this number of points are actually below the predicted 80th percent quantile. So again, there is a mismatch. We would like this curve to look like a diagonal line, just like before in the classification setting, but it doesn't in this case. The confidence intervals are not calibrated. And so we can do the same thing that we did before. We can learn a separate regression model that will try to recalibrate these confidence intervals. So we can try to basically figure out how to map predicted probabilities to empirical frequencies using a held out sort of like validation data set. So we learn a simple regression model that will learn how to map numbers between 0 and 1 to numbers between 0 and 1, so that they look more like a straight line, which is what we would like to do. That's what we would like to get. We would like to have something where the predicted probabilities match the empirical frequencies, so that we can kind of think of them as a notion of confidence. And once you're able to do this mapping between predicted probabilities to empirical frequencies, then you can basically stretch your confidence intervals by that amount, and you can get something that has the desired property. A 90% confidence interval on average will contain 9 points out of 10, which is kind of like a very desirable property if you're going to use these kind of models to figure out how to acquire data, what kind of experiments to do, or more generally to make decisions in the real world. And you can kind of see an example of why this is important. Let's say that you're building an autonomous vehicle, and you have some kind of machine learning models built in that will try to detect whether there is a pedestrian in the middle of the road. And these predictions are going to be probabilistic, and you're going to, let's say, come up with a probability distribution over the position of the pedestrian. And maybe the true uncertainty could look like the green curve. So there is a decent probability that the pedestrian is really in the middle of the road. But if your regression model is not calibrated, it might come up with it might be overconfident, and it might come up with a distribution that look like this one, right? The purple one. And if you use this model of the world to make decisions, you might make a horrible mistake, right? In this case, based on the uncalibrated uncertainty, you decided not to stop because there's no chance that the pedestrian is really in the middle of the road. Well, if you had the true uncertainty, then you would come up with the right decision, and you would say, okay, let's stop because there is a decent chance that there is an obstacle in the middle of the road. And indeed, we see that happens in real world systems. If you take some kind of state-of-the-art depth estimation model and you try to see how calibrated it is, the predictions that you get are not necessarily calibrated. And using the technique, the very simple technique that I just described, you can keep the same accuracy while at the same time making the probabilities basically more calibrated. And the same thing holds across the board if you use a number of different data sets. And what's interesting is that this is very helpful if you use these models of the world to make decisions, right? So let's say that now you have some kind of reinforcement learning agent that is trying to control one of these.
Sorry, can I ask you a quick question? What is your, I didn't catch that. What is the algorithm that you use to recalibrate?
Yeah, the algorithm is super simple. Basically, what you do is you keep a held out validation data set, you produce this curve, then you learn a regression model, which could be anything. It could be isotonic regression or just binning, to figure out how to map this curve to a straight line. Okay. And then you basically just stretch the confidence intervals by the right amount.
Okay, yeah, thanks.
And so, yeah, you can basically use it as a black box on top of any existing probabilistic forecaster. And all you need is really just a little bit of held out data to figure out how to do the stretching. And it's really, really helpful. Again, when you use this model of the world to make decisions. So here we were looking at model-based reinforcement learning, where you have an agent that is basically trying to learn how to control these physical systems, like trying to learn how to keep this pole straight, or trying to control all the joints in this little robot so that it can run as fast as possible. And the setting here is that the agent initially doesn't know anything about the physics, and it has to learn what the physics of the system basically through interaction. The system can only apply torques or apply forces to these objects, and it observes how the system behaves, and it doesn't know anything at the beginning about what are the underlying dynamics. And so one class of model of reinforcement learning algorithms are based on building a model of the world, kind of like collecting data, collecting experiences, using these experiences to build a model of the world, effectively try to estimate what is the underlying differential equation that governs the dynamics of the system. And once you have the differential equation, then it's relatively easy to figure out what is the best control policy, because if you understand the dynamics and if you understand, let's say, what is the reward function, then it's relatively easy it's just an optimization problem. The problem of figuring out what is the optimal policy is relatively easy. The problem, again, is that you typically use a data-driven model for the dynamics, maybe a neural network. And the predictions that you get from these neural networks about what's going to happen if you were to apply a certain sequence of actions, they tend to be way overconfident. The uncertainty, the estimate that you have basically about what's going to happen if you apply different sequences of actions are not calibrated. And if you are overconfident, if you tend to be, if you are too confident about what's going to happen, this might be highly suboptimal because effectively you think you know how the system works when you actually don't. And so the right thing to do would be to sort of like apply some exploration, try to do a little bit more experimentation to try to figure out what is really the physics of the system you're dealing with. But you don't do it because you're too confident on the predictions, and so that can lead to suboptimal performance. And so what we've shown is that if you take an existing state-of-the-art model-based RL algorithm, and you just add this simple recalibration procedure on top, so you just keep everything the same except that you recalibrate the model for the dynamics, you get significant performance improvements, basically as a function of the number of interactions that you do with the environment. You can look at what is the reward that you get. And basically what you can see is that if you apply this calibration, which is the green curve, to the purple one, you can significantly improve performance. You can get higher reward faster because you are interacting with the system in a smarter way, because you know what you know and you know what you don't know. And so this is an example of the importance of calibration.
So just a quick question here. So in the carpool and pusher, we see that the calibrate is above the no calibrate, but in the half cheetah, there's something that happens at 100 where calibrate really gets off compared to no calibrate. Can you comment on that, or?
Yeah, so we don't know. Half cheetah is actually, it's a pretty tough environment, and we don't know exactly why that is happening. It's a pretty complicated kind of, the algorithm that we're building on, it's pretty complicated. And we used it as a black box, literally just plugging in our recalibration on top. And so we don't have a good sense of what is going on. Like if you look at the videos of how the learning goes, sometimes it does really crazy stuff and it figures out really, really weird ways of achieving the reward. Mm-hmm. But generally our explanation, and we have many more examples on contextual bandits and other inventory control problems, where it's really about better balancing of exploration exploitation that helps.
So half cheetah is the case on the bottom left here?
Half cheetah is the one, this is the half cheetah. It's kind of like a half of a cheetah, I guess, or half, it's kind of like an animal with two legs.
The two-legged cheetah, okay, all right. Yeah. All right, yeah, thanks, thank you.
Right, and maybe let me skip this. I mean, this doesn't entirely solve the problem, as you know, there are things like adversarial examples, and if basically if you have a calibrated model, but then you apply it to data that doesn't come from the distribution you've calibrated it on, things can still go horribly wrong, as this example shows, where you add just a little perturbation to your data points and your predictions can be completely off. And so these issues still exist if you use, even if you use calibrated classifiers, because they only work if you assume that there is some kind of like underlying IID assumption that the data really comes from the test data really comes from a distribution that is the same as the one you've used for recalibration. And we've done some work on basically using techniques from online learning to be able to achieve calibration even without the IID assumption. So even against adversarial data, it turns out that you can keep the predictions calibrated without losing any performance. But I'm not going to talk about that because I think we're a little bit out of time. And so I wanted to talk about how we've been using these sort of ideas to do optimal experimental design. So using a model of the world to essentially decide what kind of experiments to do next. This is very similar to the reinforcement learning application, but in the context of optimizing batteries. And as we know, doing experiments in the real world is really expensive. It might cost a lot of money, time. Sometimes experiments are not even safe, and so we need to be very careful about what kind of experiments we do and what we cannot do. And so we've been looking into how can we use machine learning to accelerate experiments in the physical sciences. And so specifically, we've been looking at batteries. This is a collaboration with people in material science at Stanford and MIT. Batteries, of course, are huge. They're one of the technologies that are very likely going to be key for achieving a fossil fuel-free society. The Nobel Prize in Chemistry in 2019 was given to scientists that invented the lithium-ion batteries. And it's really a super important technology that we need to think about in terms of electric vehicles and smart grid and so forth. Now, one of the challenges that we see when we think about electric vehicles and using batteries in that context is that consumers want fast charging times. They would like to charge their electric vehicle as fast as the time it takes to go to a gas station and fill up a regular car. The challenge is that if you charge a battery too fast, then you're going to cause degradation, and what happens is that the battery will not last very long. You can only do a relatively smaller number of cycles before the battery dies. And so the challenge is, how do we charge as fast as possible while preserving the lifetime of the battery as much as possible? And so there are many different ways in which you can charge a battery, and generally people use multi-step approaches where they basically apply different steps where they use either a constant voltage or a constant current. And what you can do is you can apply different thresholds. You can apply different amounts of currents or different amounts of voltage over time to achieve different trade-offs in terms of how fast you charge the battery. But at the same time, different policies, different charging protocols will lead to different lifetimes. And in particular, if you apply very high currents, that is believed to increase the temperature, and that can affect the internal properties, workings of the battery. And so typically people use this kind of monotonically decreasing currents to avoid plating and basically try to avoid the degradation mechanisms that occur inside a battery. But it's not clear what is the best way to charge a battery. What kind of current, what kind of sequence of currents and voltages should you apply to charge a battery quickly without affecting the lifetime too much? And so you can imagine that there might be kind of like two ways of charging a battery. You could charge it slowly, in which case maybe the capacity over time degrades fairly slowly, or you might charge it fast, in which case maybe the capacity over time degrades a lot faster. And so the question is, what are the trade-offs here, given, for example, a certain amount of a speed at which you can charge the battery? What is the protocol that achieves the best lifetime? Or for a given lifetime, can you find the protocol that charges the battery the fastest? And one challenge here is that there is uncertainty. We are in the situation that we were thinking about before, where all batteries are different, usage patterns are going to be different, and so the kind of lifetimes that you're going to see when you apply different kinds of protocols are going to vary quite a bit. There's a lot of variability that you see here. Even if you apply the same protocol, the results that you see might be different. There's kind of like some uncertainty here among the kind of results that you can expect to see. And so kind of like the situation, the kind of toy example to think about might look like this. You have 3 protocols, A, B, C. Let's say they all charge the battery in the same time, let's say 10 minutes. But the lifetime, like the number of cycles that you can actually use before the capacity goes to below a certain threshold at which the batteries are not usable anymore, might be drastically different. Maybe protocol A, the battery can last 1200 cycles, protocol B, 850, and protocol C, 950 cycles. The challenge is that you don't know that ahead of time. And the goal is that of trying to basically figure out which protocol is the best one as quickly as possible, right? So a protocol, you can think of it as a schedule of currents and voltages that are applied just like before. Something that might look something like this. The lifetime is the average battery of the battery life for a particular protocol. And again, yeah, the goal is to try to identify the protocol with the highest lifetime as quickly as possible. In this case, try to identify that among A, B, C, you should really use A because that gives a significantly longer lifetime compared to the other 2. So the challenge, of course, is that estimating the lifetime for a protocol requires averaging over many battery experiments. So that's expensive. And a single experiment can take thousands of cycles. So let's say maybe several months. And so if you want to evaluate, there is an infinite number of protocols that you could try. If you want to evaluate just a few hundreds of them, the experiments will take many years. And so what we can do is we can, again, go back to the idea that we can perhaps use a model of the world to try to make this exploration more efficient. You can imagine that we're sort of like dealing with a row of slot machines. Each slot machine here corresponds to a protocol. We have no initial knowledge about the machines, which ones are good, which ones are not. And we need to basically figure out a strategy to exploit the machines that we know have worked well so far, but we also need to explore to kind of like gather more information about the machines, about the protocols that we have not tried before. Or another way to think about it is that, we might have 2 options. We can go to the usual place that we sort of like, we've tried before, we know it's good, or should we try something new that has no reviews, that we've never been there before, but we have no idea, and we really need to do that experiment. We really need to go there to figure out how good it is, how good that protocol is. And so one way to do it is to use a racing algorithm. Here the idea is that we're going to initialize at the beginning. We have no knowledge about how the protocols work. So we initialize all the predicted performance of the protocols to some constant value with very large confidence intervals for all the protocols. We have no idea about how well A, B, C, or D, A, B, or C works. And then we will basically just start doing random experiments, updating the confidence intervals as we collect more information about how the protocols work. After a certain number of experiments, we might get
just a quick question. Is there, this is purely experimental, or there's a way to use computer models for that? Because it seems pretty expensive to do random experiments, or difficult. So
we'll get to how to incorporate models with the experiment.
That's
kind of like our contribution. Yeah. So if you just do experiments, what you do is at some point you figure out that maybe protocol C is very likely to be worse than, let's say, protocol B and protocol A. So your bound on the, given some threshold, you have a bound on how well C can perform. If that bound is less than the lower bound on how B performs, then you're fairly confident that C is worse than B, and so you can eliminate it. You don't need to consider C anymore. And then, you still don't know which one to pick between A and B because the confidence intervals are sort of overlapping. So you can do more experiments until you get to the point where you can confidently say that A is better than B. And at that point you eliminate B and you end up with your situation, your solution that A is better. So the goal is to minimize the total number of experiments. The challenge is that each experiment will still take you about 2 months, so it's still very expensive. So how can we accelerate that? Our idea is that we can use a model to basically try to predict the outcome of an experiment before it's even completed. And the situation looks like this. You can imagine running an experiment in the real world from the beginning to the end, in which you collect this kind of capacity curves and you see that the lifetime is a certain value. Or what you can do is you can run the experiment for a little bit and then try to predict what the outcome will be using one of the forecasting models that we talked about before. And the advantage is that you only need to run the experiment for a little bit and then you can come up with the predictions very quickly. And the challenge is that you need to figure out how to update the confidence intervals when you're dealing with both. When you have a real experiment, then you always know that the confidence interval will go down. When you use predictions, well, whether it goes, the predictions might be too uncertain to basically allow you to rule out an experiment, right? So let me show an example here. Maybe you are experimenting with C, you run it for a little bit, then you make a prediction for what's going to happen. But if it is still the case that this confidence bound doesn't shrink enough, like if it is the case that it shrinks enough with the prediction, then basically what you can do is you can directly remove C without ever completing the experiment. Oops. Without ever completing the experiment. If, on the other hand, the prediction is too uncertain and you're not confident about what will be the outcome of the experiment, then what you need to do is you basically need to run it longer until you're sufficiently confident about what will be the outcome, until basically the confidence interval will shrink enough that will enable you to make a decision and let's say that B is definitely worse than A, and so you can remove it. And the nice thing, I think I'm sort of running out of time, so I'll go quickly through this, but you can prove some nice guarantees about this this kind of algorithm, in the sense that it's still accurate and it takes less or the same time than just doing real experiments, basically depending on how good your predictive model of the world is. And you can extend it to some practical variants, like running experiments in batch, where you don't do a single experiment every step, but you run multiple experiments, and other variants. So at the end of the day, the system that we built sort of looks like this. We have many batteries. We have 48 batteries that we can basically test in parallel. For each battery, we can try different set of charging protocols. As we run the experiments, we collect data about how the battery is performing. We use this machine learning system to basically predict the outcome of the experiment before it is even terminated. And then we have this optimal experimental design pipeline, the racing algorithm basically, that will determine what kind of experiments to do next. And this is something that we've been running for the last few years in the real world with the people in material science at Stanford. And the results is that it's very, very effective. This is a paper we published in Nature a few weeks ago. We've shown, for example, that if you were to test, we did this benchmark where we tried 200 protocols that would have taken 1.5 years to basically evaluate each one of them separately. We were basically able to quickly find the best solution among these 225 protocols in 16 days using this combination of predictive models and optimal experimental design. So a huge performance improvement in terms of the number of the experiments that we need to do. And we were able to find some really good charging protocols using this approach. If we compare the kind of protocols that were obtained by this automatic closed-loop optimal experimental design algorithm with state-of-the-art methods, patents from Tesla, previous papers, things like that, we find that the predictions that come out from our model are fairly accurate, and we are actually able to identify protocols that are better than the ones that were proposed in the literature, and we can do it much faster, right? Using this combination of data-driven modeling and optimal experimental design, we were able to very quickly, in only 16 days, a little bit over 2 weeks, identify some really good charging protocols. And yeah, so of course, there's many other applications of this kind of ideas. This combination of dealing with uncertainty, combining simulations and experiments, I think it's pretty exciting, and it has potential to be applied to many other applications. I just want to mention briefly another application where we've used this kind of ideas, up at Slack, where we've used the similar ideas to figure out how to tune these big magnets that they use to tune the beam. So LCLS is like a free electron laser. It's a really expensive $400 million machine, 2 kilometers long, really complicated, and there are many parameters that you can tune to get good performance, where performance here is basically the energy that they are able to get with the beam. And the problem that we looked at is basically how to tune these big magnets, these quadruple magnets, to get very quickly high energy. Currently, or before we did this work, people used to optimize these parameters by hand. They would spend a lot of time basically tuning and trying to figure out good configurations that would give you high energy. And that's very wasteful because beam time is so expensive and it's a very, very limited resource. Everybody is fighting for beam time. I think they were estimating it might cost thousands of dollars per minute to do an experiment, and they would waste a lot of time trying to manually tune parameters. And using similar ideas, basically Bayesian optimization style approaches, you see here a live demo of how we are basically controlling all these magnets using our algorithm, and we are able to very quickly find configurations that would give you high performance much faster, like 4 times faster than what human operators typically are able to do, and better than other kind of like straightforward baselines that are also sort of automated. We have a paper coming out accepted on physical review letters on this, and some machine learning papers where we'll actually develop some new algorithms to deal with this. And this is a technique that people are starting to apply to other kind of particle accelerators all over the world, because it's really pretty powerful, and it seems to work quite well in these kind of applications. So I'm out of time, so let me skip. We've done other applications to designing proteins, to fluid simulations, but I'm gonna skip that. I'm gonna skip the prior knowledge, and yeah, I just wanted to conclude and again talk briefly. Summarize. We talked a bit about how to model uncertainty and why that's important when you think about ML systems in scientific applications, like figuring out how to design experiments to acquire knowledge and to figure out how systems work or optimize some kind of like design space. There are interesting questions in terms of combining data with prior knowledge that I haven't talked about, but I think this is a really exciting kind of problem also in the AI space, because it involves induction, deduction, constraints, physical theories, limited data. There's all kinds of interesting opportunities for developing new AI and machine learning models in this space, and also have the potential to have impact on interesting real-world applications like batteries, particle accelerators, and so forth. And I think I'm about out of time, so if there is a few minutes, I'm happy to take questions.
Yeah, actually, I have a question. Can you go back a couple of slides to your racing algorithm? So what's the optimal design? What is the algorithm you use for optimal design? I didn't catch that.
Yeah, so it's basically the basic variant is like a racing algorithm where you basically keep trying out your protocols and you eliminate protocols that are clearly worse than one of the ones we have. And our contribution is that basically we incorporate predictions. So we don't necessarily complete an experiment, but we guess what will be the outcome of an experiment based on a model.
So you have another neural network that is in charge of making this the simulated prediction.
Yes, so it's actually not even a neural network. It's a simple linear model. It's a Bayesian linear model, because we don't have a lot of data, so we actually use simple models. But yeah, basically there is a model that predicts the outcome of the experiment as we go. And so instead of basically thinking of experiments as being atomic units, either you do this experiment until the end or not, you are allowed to run it until you have a good guess about what's going to happen, and that can save you a lot of time, basically.
So it's a linear map. This is the prediction that you optimize.
Well, it's linear on a set of handcrafted features. So our collaborators came up with some highly nonlinear, pretty complicated features of this time series. That were informed by their knowledge of how the battery works internally, and then it's just a simple linear model that works pretty well, so we just use that. But yeah, it's based on complicated.
And the model is sort of refined or trained as you acquire data.
Yes.
Right. Okay. Yeah, I see.
Yes.
Okay. So. Thank you.
So are there more questions from the group? I have kind of a basic question. So our area of interest is a lot of times is field campaigns for collecting data, buoys or observations that are expensive for things like bathymetry. I mean, how good do your models, your predictive models have to be? Is that something that I don't have a feel for how well this would transfer over to that kind of setting?
Yeah, I mean, that's a good question. I think we know that there is some sort of like no free lunch here, where the models are good. Getting improvements. I think the hope is that you shouldn't be doing worse than using no models at all. I think the interesting question is, how do we? I think the kind of like disappointing state of affairs is that kind of either you do it purely data driven, in which case you're completely forgetting about all the models that you might have, all the simulators, all the in these batteries, or and we don't have a good way of kind of like combining these two things. Research on how to incorporate good priors from the literature.
The sound is the sound okay?
I hear a lot of noise.
Yeah, you're very cut, yeah.
Okay, I muted. I think someone else was not on mute. So yeah, make sure you're on mute if you're not asking a question.
Yeah, for your question, Matthew, about bathymetry, so do you have a, yeah, I mean, the idea of combining experiments and simulation, of course, is very attractive. Do you have an idea of a type of optimization that could be done in this, like, do you have something in mind in terms of optimization with for the applications you're interested in?
Well, for us, some of these are these longer term experiments where we maybe are putting sensors into the water to monitor them, and you would like to use as few as possible. So maybe, and I don't have a good idea right now of the specific methods. Go ahead.
So for the LCLS application, we actually used, so they had a simulator. I think apparently the thing they used to build the whole machine, they had a simulator that they used to design the machine. And so we were able to basically incorporate it somehow by basically coming up with a kernel that is consistent with the simulator. I mean, again, it's not, I don't think it's the perfect solution, but at least we were able to jumpstart so this is based on a Gaussian process, and the kernel was kind of like inspired, was trained on data from the simulator. And so at least we were able to take advantage of that to some extent.
Yeah, I have one question about some experimental design. It's a really nice kind of talk and quite applicable for very complex testing problems. And I'm from earth science, geoscience divisions. I mean, obviously our material, like in battery, probably our material much more heterogeneous than battery typically, particularly the testing protocols, we never have similar samples. And for the case, we always need to consider this uncertainty bound. I think you explained this with a confidence interval at the beginning of presentation. How do you match those uncertainty from experimental data versus some uncertainty from numerical simulation? Certain numerical simulation may have a lot of kind of uncertainties from model as well as parameter space.
Yeah, that's a good question. I think for most of our work, we've been using basically focusing on machine learning, so data-driven models, where we're basically using the data itself as a way of trying to calibrate the uncertainty. And I think ultimately, that's probably the only way to do it, to sort of like look at unless you have really good priors, that's always kind of like tricky. So I think, I mean, I'm not an expert on physical on simulations, so I don't know, especially not in the earth sciences. But I think ultimately the way to do it is to collect data and use the data to kind of like inform how confident you should be or you shouldn't be in the predictions. And that's kind of like the problem, that maybe getting the data is expensive, so you need to be careful about how you do it. But that's my feeling, or that's how we've been using it, always basically using held out data to kind of like bootstrap our estimates and figure out how confident we should be in them or not.
For example, we could imagine a situation where you have some, the held out data is actually just coming from experiments, and then you're, generating your CDF from simulation, and then applying your stretching and correction, so that you can, correct your simulation, your simulated predictions with the, so it matches the whatever experiments you have.
Yes, that's for sure. Yeah, we make no assumptions on how the structure of the model. It could be a simulator, it could be a neural network, it can be anything. It could be a Bayesian model, it could be dropout, it could be an ensemble, it could be, and we've looked at many such cases and we've shown that no matter how you get your uncertainty, you can always try to make it match basically
Right.
the physical world by using these kind of simple techniques.
All right. Well, thanks again. I guess let's go ahead and since we're a little bit over time, that Beijing, are you there? Can you go ahead and start?
Yes.
Thanks again, Stefano, for your talk.
Yeah, thanks for inviting me.